All right, welcome to Bit by Bit, episode 9. In this episode, we're going to go through some of the content of chapter 6, I/O using monitor and keyboard from assembly lines. Let's kick it off and just get started. So a quick review of what we know so far and where we learned it. We learned about JSR and RTS, jump to subroutine, return from subroutine. And I talked about orthogonality a couple of episodes back. I was a little naive. Orthogonality it has more to do with the different modes you can call instructions with, whether that be immediate or absolute or zero page and that kind of thing. So the 6502 processor doesn't have a really solid orthogonal set, and a lot of different instructions work with different modes. But what they do have is a lot of complementary instructions, and that's what we're talking about here. So these complement each other. You jump to subroutine, you return from subroutine. And that was all in the first real chapter after the here's what an apple is. These have to do with calling subroutines, and typically we're going to be calling the subroutines that are in the, where's the book? Here it is. That are in here that it talks about specifically with respect to the firmware, the monitor. So the bell routine, the character out routine, the paddle read, those types of functions. We're going to call those in our own that we write. So if we write a subroutine and put it into memory at like 8020, then we can call JSR 8020, and it's going to jump there. And if there's an RTS there, it's going to know where to come back to. So that was the first thing we learned. Then we learned these 6 instructions. Really, there's kind of working with the accumulator, the X register and the Y register, loading and storing. So they're complementary operations. So we learned 6 new instructions with a total of 8. The next chapter, in chapter 4, we learned about increment and decrement, and we remember that these in the 65CO2 more modern enhanced processor, they do support the A register, but in the old version of the Apple II, they didn't. So we stick to a straight 6502 and pretend as though they don't. So we use increment and decrement against memory, not against the A register. And then there's the X and Y registers have the increment and decrement. Then there's, we learned about the branch not equal instruction when the 0 flag was clear, then we would jump. Branch not equal, yes, that's true. All right, and then in chapter 5, we learned about branch when it's equal, so when the 0 flag is set. And then we learned 2 sets of transfer instructions, one for the X register to the accumulator and vice versa, and one from the Y register to the accumulator and one from the accumulator to the Y register. And then we also learned the unconditional jump instruction. We noted that there wasn't really a complementary instruction to jump. I kind of said that maybe it was no op, but that's probably not true. And then we get to where we are right now, which is chapter 6, where we're going to pick up. We're going to learn a little bit about compare, branch when clear, branch carry clear, and branch carry set. That's a mouthful. And then compare the X register and compare the Y register. And these are sort of complementary. But while we're here, we should note that there's 56 instructions, and I've rewritten them all here in functional groups based on Obelisk's work over here at the at his website. So, or hers, who knows. But this is where I got it from here. It's a really nice, concise set. Talks about them. If you click on one, you can see sort of the flashcard for that one. All right, but the reason I want to kind of go over them again is to see that the distance between our 21 instructions that we know about now, soon to be 26, is really, there's not a huge amount of distance between those 26 instructions and the full set. So let's figure it out. So there's a set of load and store operations that we already know all these, the load and store for the A, X, and Y registers. There's the transfers from registers. We know those. That's 4 more. There's stack operations. We haven't really talked about these yet, but we will. There's 6 of them. Transfer the status to the X register, transfer the X register to the status register, push the accumulator onto the stack, pull the accumulator from the stack, push the processor flags onto the stack, stack, and pull them from the stack. That's all those are. And that kind of, once you've heard them said that way, they make a little bit of sense. But later, when we need a stack, they'll make a lot more sense. So that, we'll hold those in abeyance. And then there's the logical operators that we haven't really touched yet, but we will. The and, the or, these both work with the, well, they all work with the accumulator. That's what the A here is. And then exclusive or and bit, which is a test of bits. And then we have some arithmetic operations. We'll start getting into these pretty soon. Add with carry, subtract with carry, compare, which we'll get into today. Compare X and compare Y. And so here we don't really know these yet. We don't really know these yet, but they kind of make sense. We don't know these yet. But now we're going to get into stuff that we kind of recognize well. We will in a minute. And then we have a shifts, some shifts, which is arithmetic shift left, which takes the bits in the register and just bumps them one to the left in the ASL instruction and pull in a 0. And logical shift right, which bumps them all to the right and bumps one out into the carry. And then rotate left, which kind of uses the 8 bits of a register plus the carry flag and rotates around in a circle. The bits get, a bit gets taken off the end and it gets put on the other end. And rotate right, same sort of thing. And then we get into stuff that we do know. So jumps and calls. We know the unconditional jump. We know the jump to subroutine and return from subroutine. Status flag changes. We've not yet seen a bunch of this yet, but you can imagine that this isn't terribly complicated because we have clear carry, set the carry flag, clear the direction flag, set the direction flag, clear the interrupt flag, set the interrupt flag, and then clear the overflow flag. No telling why there's no set the overflow flag, but whatever. It is what it is. And then we get 3 system functions, and that's it. We got the break, which is 0, in machine code, and it causes the CPU to stop executing. We got the no op. We haven't seen that yet, but that's just an instruction to, it allows the program counter to get bumped by 1 without anything happening. And then return to interrupt, RTI, return from interrupt. And that's it. That's all there are. So the distance between this list and the list we already kind of know is not that far. So I wanted to kind of touch on that. Now, let's just get into what we're going to do in this episode in terms of coding. We're going to code to trap the mouse. We're going to use the mouse as our paddles equivalent, and we're going to look for when the mouse returns signal that is in the A to Z range. So basically, like as though you typed an A or B or C or so on and so forth. And it does. When you move the paddles, there is an A to Z in there. So we'll see it. We're going to use the compare to test for a range, basically somewhere between A and Z. That's our range. And the way it does this is it instructs this compare instruction subtracts contents of memory from the contents of the accumulator. So we're going to put a keystroke somewhere, and we're going to compare that with a value in the accumulator. And it's the symbolic notation, what we put on the index card, if you will, is A minus M. Okay, and just like it says, it compares the value of the accumulator against memory. And here, this is a non-intuitive kind of idea, at least it is for me. And so I take best notes I can, and then I try to work it out. So what this is going to do is it's going to compare the accumulator against this value in memory, and it's going to set the Z flag if the two are equal. Right? So if you subtract one from the other, what's the result? If they're the same, nothing, 0. Right? Otherwise, it's going to set. Otherwise, it's going to reset Z. So it's which is clear Z. It's going to set it to 0, and then it'll set the carry flag if the accumulator, what's in the accumulator, is greater than or equal to memory. Otherwise, it's going to clear carry. These are the 2 critical pieces. It messes with the negative flag too, but it's not. We're not using that really for any kind of jumps or anything. And the mnemonic I use, the mnemonic that keeps it straight for me, comes from Lancaster's book, and it says big A sets. Okay, so if the accumulator is big and the other value is small, it's going to set the carry flag. That's how we can remember it. So what that means is we can branch carry clear when the accumulator is smaller than the memory. And we can branch carry set because it only gets set when the accumulator is greater than or equal to memory. All right, so we're going to do some work in the emulator here, and I've already kind of mapped it out here, but we're going to start it up. And hopefully I've disabled beeping because that is kind of annoying. All right, and we're going to just quit out of the assembler, get back to basic, or just don't boot it, whichever one you like. But it says let's put 22 in the accumulator, so we're going to call 151, negative 151, which is the monitor. And once we're in the monitor, first off, we're going to hit Control E and Enter. It's going to show us the values that are currently in the registers. So the A register has the value C0, X is 0, Y 0, the status flags are 0, and the stack is EC, whatever. We don't care about anything here other than what's in the accumulator and what's in the status flags. All right, so, but these flags also exist in memory. So if I go 45 dot, let's see, 45, 46, 47, 48, 49, 49, 45.49, we can see the same value, C0, 0, 0, 0, 0, 0, 0, EC. Okay, and we can change those values too from the monitor. So we're going to set the accumulator to 22. It's a nice convenient value to compare things to. So I'm going to set the accumulator to 22, 45, 22, hit enter, Control E, enter, and I can see that I changed the accumulator. All right, and then we're going to put some values into memory. And we remember from the last episode that these values of memory are safe. They don't conflict. They don't overwrite anything in integer basic, floating point basic, or the monitor or anywhere else. So we're just going to put these values starting at 0, 6. So I can type 0, 0, oops, wow, that's really convenient. I can come over here and type 0, 0, 6, colon, and then 11, 20, 22, 33. And then we can look at them through 6 to 9. 6 to 8 would have been okay. 11, 22, 33. Okay, so they're in memory. A 22 is in the accumulator. So I'm going to compare each of these to that value. And you can see that the first value, the 11, is smaller than 22. The 22 is equal to 22, and the 33 is greater than. Okay, so the three possibilities. And to do this, what we're going to do is write some machine code to basically compare each of the values in memory. So I looked up in the book, which is, let's do it this way. Wow, there's a lot here. None of this looks like the book I need. Okay, here it is. Okay, I looked up in this book, down here at in the appendix. There we go. We were there. Okay, into this section here. If I can make things smaller. There we go. Sorry, dog. Wow, some kind of snap. My bad. Apologize. What I'm intending to do is to look up these compare codes. So we're going to look up the instruction compare right here. And we could compare with immediate values, but we're going to compare with memory, which is either a 0 page or an absolute. And I chose 0 page because they're on the 0th page. It's like the 6th byte on the 0 page. So I used the 0 page instruction and I did C5. And then the second byte is the 06, 07, 08. So there's my opcode that I opted for, the C5. We could have done absolute, but then we had to supply 2 bytes. And I just wanted to supply the 1. So that's how I got this. So this is the byte codes that I'm going to enter in. C5 is the compare, and it's compare with what's in page 0 at byte 6. And then I do a break, which is 0, 0. And then we have compare with what's in memory 7 with a break, compare what's in memory 8 with a break. That's all that means. So let's type that in. Yes, that'll make you nauseous. My bad. All right, we type in 300 and then colon and then the bytes we want to change. So C5, 06, 00, C5, 07, 00, and C5, 08, 00. And then we can list it to see what it disassembles to, all right, which is compare 6 and then break, and then compare 7 and then break, and then compare 8 and then break. And I'm going to call each of these little miniature routines, like the first one, which is going to compare it with 06, and we're going to stop and look at the registers. So I'll call 300G, and then I'll call 303G, and then 306G, and we'll see what we get back. All right, so 300G, and we get the accumulator still contains 22. The memory that we messed with still contains what it contains, and we can take a look at that. Let's see, 6.8, right? 11, 22, and 33 still contains that stuff. But after we've done the first comparison with this 11 and this 22, we get a processor status flag of 31. And we'll keep track of that. We'll look at it in a sec. But let's go ahead and run the next one, which is 303G, all right, which is going to compare the 22 with the 22, and it's going to get a processor status flag of 33. And then finally 306G, third comparison, which compares the byte in 8, which is 33 with 22, and it gets B0. How do we interpret that? Because these are the processor status flags, 31, 33, B0. Well, I've broken it down a little bit for us already. So we're gonna look at it, and the bits of the processor status flag are broken out like this. 2 nibbles. One has the negative flag, the overflow flag, an unused flag, the break flag, which none of that. The negative flag is used, but we're not caring much about it. And then that is not a C, that's a D, I think. There we go. That's the direction flag, the interrupt flag, the 0 flag, and the carry flag. Okay? And so we take the number 31 and we say that's 2 bytes. The 3 this is 3 in binary. Okay, so the break flag and the unused flag are set. And then on the byte, the nibble we care about, it is a 1, which means the only thing set is the carry flag. All right, and let's make it. There we go. Move this over. Okay, and so what we can parse this into is that when it's 31, the negative flag is 0. The 0 flag is 0. The carry flag is 1. Those are the 3 flags affected by the compare. And what that tells us is, since carry set, accumulator must be greater than or equal to, because we remember that from back up here. The accumulator is greater than or equal to memory. That's when it sets, because big A sets. And we're going to primarily be concerned with carry flag, although the 0 flag might be interesting. Okay, so when the accumulator is 22, and the value we're comparing it to is 11, that means 22 is greater than 11. So sure enough, the carry flag gets set. But what happens when it is 22? 22 is equal to 22. Well, the carry flag still gets set because it's greater than or equal to, and the 0 flag gets set. So we can differentiate the two if we needed to with the 0 flag. And the breakdown is you got 2 3s. So this is binary 3, and this is binary 3 for each of the nibbles. And then we have B0. Well, B is, A, B is 11. Is it really? A is 10. A is 10. I think I kind of blew that, but it's more like that. All right. The B is 11. A is 10. B is 11. So 8 and 3 make 11. So this is more correct. The negative flag is set, and so are some of these others, but none of the others are set. Okay, so when the value in the accumulator is still 22, when the value in memory it's comparing to is bigger, then the carry flag gets cleared. All right, and just to be sure that we are that what we believe to be the case is really the case, we're going to reverse the memory values and rerun the comparisons against these. So they should reverse. It should go 33, 11, 22. And this should go B0, 33, 31. All right, so let's just test it by changing the memory location. So 33, well, let's look at it. 6 to 8 is 11, 22, and 33. And now we're going to set it, and it's going to be 33, 22, 11. And we'll look at 6 to 8 again. And sure enough, we flip the bytes, okay? We don't have to change our code because it's just testing those memory locations. So when it tests against 33, it's going to get that result, and then 22, and then 11. So we can do exactly what we did before, 300G, and we get B0, which is this one, and then we run it 303G, 303, yeah, and that gets us 33. And then we go 306G, and it gets us 31. Okay, and if we parse those out, they're the exact opposite of the ones that we ran before, so it works. So what that tells us is that the compare indeed will return, it'll get set, carry flag gets set if the accumulator is larger than or equal to. And so we can use that to write our little program. So let's think about that. Book has the code. It is presented with little fanfare, but it's quite sophisticated. So let's kind of think it through. So we'll write the program to read the letters A to Z from the paddles. In this case, the mouse, and it's really the paddle because you get to pick one. When we put the 0 in the register A and then call pread, it reads the first pedal. So and in our case, it's going to be our mouse. And then Appendix E of the book says A to Z is C1 to DA. So let's, while we're here, let's see, Appendix E. It's got to be getting close. There we go, Appendix E. All right, when we look at these values and we're trying to make sense of this, there's a couple of things going on here. One is that ASCII is usually a 7-bit code, but Apple cares about 8. And so it allows for a lot more represented characters than the average ASCII character set. But when we look at this list, we're interested in this key section here, and then maybe a little bit about this screen thing. So right now, none of these are keys that we care about. None of these are keys. Yeah, they are keys. Where are they? Okay. Okay, yeah, I'm not entirely sure what that is. But here's the ABCs, but they're inside of the square brackets. And it tells us that inverse characters are surrounded by brackets. So these are inverse characters. We don't want to really trap those. We could, but we don't want to. And then there's these that are with the angle brackets, and it tells us what the angle brackets is. Flashing characters by angle brackets. That's nuts. We don't want to have flashing characters on screen. But if we keep going through this list, eventually we get to some that look a little bit like this. These are control characters. So these aren't ones we're really interested in either, even though they'll have normal representation. They're control characters and they mean different things. All right. And so we keep going down the list and keep going. And we wind up eventually coming to a regular looking A and a regular looking A. And that's where we care about. That's our A. That's C1, which is 193, is our uppercase A. All right. And we're only concerned about uppercase for right now. All right. And then we go down here to Z and we see that it's DA. So the range between C1 and DA is A to Z. And that's what we want to capture. When we're P-reading the mouse signal, we're only going to print it out when it's one of these characters. All right, and that's what that's all trying to tell us. So A to Z is C1 to DA. We're going to read a value from the paddle. And if that character is less than A, then it's, meaning less than C1, it's going to loop and go get another character because we're going to ignore anything less. Anything less would be in this list up here, and it's not an A through Z. So we're going to ignore those and try to go get another one. All right. If the character is greater than Z plus 1, meaning DB, okay, if it's greater than the value of Z, which is DA plus 1, all right, then again, we're going to ignore it because that's all. If it's greater than that, it's not A to Z either, so it's going to go back and get another character. But if it's in their range, then we're going to print it out. And once we print it out, we're going to loop again forever. All right. So the code that we're talking about only prints A to Z and nothing else. It loops forever and it works great. That's the theory. So, wow, where'd it go? All right, let's type it in and see what gives. I'm going to return to basic, and I'm going to retype assemb. And now we're back in the assembler. I'm going to change the drive to 2. I think I already typed it in, but we'll see over here on the Merlin work disk. I'll do a catalog and see if there's one. Paddle 2, yeah. So we're gonna load up paddle 2. You're gonna have to type it in. So I'm gonna load source and it's gonna be called paddle 2. All right, and then we're gonna list it and see what we've got going here. So this is straight out of the book. I typed it in. You should do the same, but basically we set org to 300 because that's where I want to run it from, which is call 768 in basic. And I took out the OBJ thing because it's really kind of not necessary for us to have one at all, ever, at least for these little tiny programs. We just need the org, and we're doing it in the full screen mode. So we got the origin of our code. It's going to sit at 300, the bytes that get assembled and loaded. And then, excuse me, we have pread, which is one of our monitor functions. It's located at FB1E. We have home, which is equal to FC58, that's clear the screen. We got cout to print out our characters at FDED. So these are our 3 little monitor routines we're going to call. And then we set a start label. We jump to subroutine home to clear the screen. And then we load the X register with 0, 0. So I said the A register earlier, I meant the X register. And when it's loaded with 0, 0, that tells it to read the first paddle. And since we're going to set that first paddle to be the mouse, it's going to read our mouse. Then we're going to loop. We're going to start the loop. And what we're going to do is we're going to pread. We're going to read a byte from the paddle or from the mouse. And once we do that, we're going to transfer that character that we read into the accumulator. So it'll get the 22 we were looking at a minute ago. All right. And then we'll compare that value with C1. Okay. And remember, when we do a comparison, it's going to, if the accumulator is bigger than our compared value or equal to it, it's going to set the carry flag. So what this is saying is that we're going to compare C1 to the value that we read, okay, from the character that we read off the mouse. And if it's less than, or if it's, if the, I'm going to put it over here so we can keep track. Let's do the math. All right, we're going to compare C1. Pound dollar C1. So that's the memory part with our pound dollar, is that right? Yeah, pound dollar C1 with the accumulator, which is our red character, right? And so A equals whatever ours is. Let's say that it's less than, let's say that it's less than A. So it's whatever character is less than A. We're going to do that comparison, and when we do, if the accumulator is bigger, if C0 is bigger than or equal to C1, then it's going to set the carry flag. So it's going to branch on carry clear. So it's not getting set because it's not greater than or equal to. So it's not getting set. It goes to here and reads another character. But if it is, if we get C1, then it's going to compare those and it's going to find out that they're equal. Or if it's C2, it's going to find out that the accumulator is bigger. So it's going to set the carry flag. And so it's not going to branch on carry clear. Right, but it is going to compare it then to DB, to pound dollar DB, which is Z plus 1. Pound dollar DB, which is Z plus whatever one character past the ZB past Z in the ASCII code. Right, and it's going to compare that to what's in the A register, which if it's C2, it's going to find out that the accumulator is smaller than what's in that memory byte, and it's going to branch on carry set, which is the exact opposite, right? Before we branched on carry clear, was it less than? Now we're going to branch on carry set, is it greater than? And it's not if it's C2. But if it ever gets to Z, it's still not going to branch on carry set. But if it's Z plus 1, whatever that is, let's just pretend it's a percent sign or something, okay? If that's the case, well, I guess Z plus 1 will be DB. Okay, if it is equal to DB, or better yet, TC, it's gonna branch on carry set to the loop and go get another character. So if it gets past this, it means it's a valid character. And so what does it do with a valid character? It couts. It prints out the character and it continues the loop. It's an infinite loop, which is nuts, but that's why we put the comment. And then I turn the listing off. But let's assemble it, see that it works. All right, it works. There's the bytes that are going to get put at 300. Just kind of remember, let's take, I'm going to put a few of them here. 2058 FC, and then A200, just so we can see that when we get around to looking. All right, and we'll play with that a little bit. So there it is, it's assembled. It's actually saved on disk, so I'm not going to do that again. It's ready to run. Now, let's quit. Let's quit out of here. We're in basic. We can call 768. No, we can't do that yet. There's nothing at 300. If we were to print peak 768, that's 197. That is not anything to do with 20, even in hex. Okay, so that's just, it's not there yet. We have to beload it, and it has to be saved on disk for you to beload. So be sure to save it. I guess I already did, but it's called paddle 2. All right, now hopefully print peak 768 is more like 32. Yeah, which is 20. Okay, 20 hex is 2 times 16 plus 0, which is 32. All right, so there it is. It's in memory. It's ready to run, but I'm not capturing the mouse right now. Let's go ahead and get the mouse captured. So I click on my little joystick, go up here to input, where it says joystick 1, that's paddle 0. All right, we're going to pick the mouse. Remember, control, left control click is the getting out of there. Control with the left mouse click will get you uncaptured, but I'm going to capture my mouse, and we notice that the cursor goes weird, and I get the 4 little white level marker things. Okay, which show me where my cursor is on screen. Now I can run paddle. I can run the code that I want to run, but I can do it by call 768. All right, and as soon as I hit enter, I'm going to start moving the mouse. There it is. Nothing's happening. Oh, I move it. You can see that the letters that are being presented, that are being printed when they print, and there are not a lot of them printing, but they are only the letters A through Z. Okay, and then when I don't move anything, it keeps repeating that. Control, break, will stop all that. All right, so that worked, and that was interesting. Let's reset the mouse to that numpad. I have a on my keyboard, I have a num lock and some numeric keypad. You probably do too. If you do, this will work. If not, it's going to be a little weird. Just ignore it. But I'm going to hit Control left mouse, and then I'm going to turn that off. So go to the mouse, pick the number keyboard numpad. You can probably try cursors too. All they're doing is simulating joystick control. So I'm going to take keyboard numpad, click OK. I'm going to call 768 again. And this time I'm going to press the numeric keys. Let's see if I can get any of that. It says nothing about A to Z on that one. All right. And nothing else will do it. So control break on that. So yeah, the mouse is more analog, so closer to what joysticks are doing than the numpad. But that's it. I'm going to call it on that for part 1. In part 2, we're going to look at keys and strobes and stuff like that. And we'll see you next time. Thanks.